Electricity feels obvious. Flip a switch, light appears. We think we know what's happening. But what if almost everything you imagine about electricity is wrong? What if nothing is actually flowing the way you think it is? There's a famous idea that completely breaks the picture in your head about wires, electrons, and energy itself. Once you see it, electricity stops being a thing and it starts being something much stranger.
Outline 1.
Electricity is motion, not stuff. When most people hear the word electricity, they imagine a thing, a kind of invisible fluid, something that sits inside wires and flows out when you flip a switch, like water waiting in a pipe. That picture feels natural, it feels simple, and it is almost completely wrong. Electricity is not a stuff. It is not a substance stored inside the wire like juice inside a bottle. Electricity is motion. It is a pattern of movement. And once you see it that way, many confusing things suddenly become clear. Let's start with the wire itself. A metal wire is already full, completely full. Inside it are trillions of electrons, all packed together with atoms. When the light is off, those electrons are not gone. They are already there. Nothing special has been added. The wire is not empty, waiting for electricity to arrive. Now you flip the switch. The light turns on almost instantly. Not after seconds, not after minutes, almost immediately. But here is the strange part. Individual electrons move very slowly, really slowly. In many cases, slower than a snail. If electricity were a stuff traveling from the power plant to your bulb, the light would turn on much later, sometimes minutes later. But it doesn't. So what is moving? Think about a long line of people standing shoulder to shoulder. Nobody is walking forward. Everyone is already there. Now imagine someone at the back gently pushes. That push travels through the line very fast. Almost instantly, the person at the front feels it, but no one had to run from the back to the front. The motion moved, not the people. Electricity works like that. The electrons are already in the wire. When you turn on the switch, an electric field appears. That field pushes on electrons everywhere at once. They all begin to drift together, very slowly. Yes, but the effect spreads fast. So electricity is not electrons flying through space like bullets. It is coordinated motion, a shared response, a pattern that fills the entire circuit. This is why a circuit matters. Electricity is not something that leaves the battery, travels to the bulb, and disappears. The circuit is a loop. The motion happens everywhere in that loop at the same time. Break the loop and the motion stops. Now let's talk about energy, because this is where many people get even more confused. When a light bulb glows, energy is being delivered. But that energy is not carried by electrons like tiny delivery trucks. The electrons barely move. What actually carries the energy is the electric field around the wire. The field stores energy, the field moves energy, the field does the work. The electrons respond to the field, bumping into atoms inside the filament, making them vibrate faster and faster. That vibration becomes heat. And when it gets hot enough, it glows. Light appears. So again, electricity is not a thing flowing through the wire. It is a process, a relationship between charges and field. This idea explains something that feels magical at first. Imagine a very long wire connected to a battery and a lamp far away. When you close the switch, the lamp lights almost instantly, not because electrons rushed from the battery to the lamp, but because the electric field changed everywhere along the wire. The field changed the rules of motion, and the electrons responded locally. Now notice how different this is from the water picture. Water must physically travel. Electricity does not. The water analogy is useful at the very beginning, but it breaks down quickly. It hides the most important idea. Electricity is about how charges influence space around them. This is why insulation matters. This is why spacing matters. This is why shape matters. The behavior of electricity depends not just on what is inside the wire, but on the space around it. Think about static electricity. You rub a balloon and stick it to a wall. Nothing is flowing through a wire, yet forces appear, motion happens, fields rearrange themselves. Again, electricity without stuff moving from one place to another. But think about lightning. Charges build up, fields grow stronger. When the field becomes intense enough, the air itself breaks down. A sudden violent motion occurs. Enormous energy moves, not because electrons traveled calmly like a river, but because the field changed explosively. Once you start thinking this way, electricity becomes less mysterious and more beautiful. You stop asking where does the electricity go, and start asking how is motion organized here. You stop imagining storage tanks of electricity and start seeing patterns of cause and effect. Even a battery fits this picture. A battery does not contain electricity waiting to escape. It contains chemical energy that can create an electric field. The field then sets charges into motion throughout the circuit. The battery is more like a rule maker than a container. This also explains why electrons don't get used up. You don't run out of electrons. You run out of ways to push them. You run out of energy to maintain the field. So when someone says electricity flows, that's not entirely wrong, but it's incomplete. What really flows is influence, coordination, energy carried by field. Electricity is motion without travel, action without transport, change without stuff moving from here to there in the way we expect. And that idea shows up everywhere in physics. Heat, sound, waves, even information. Often what matters is not things moving long distances, but patterns moving through systems. Once you see electricity this way, you realize the wires in your walls are not highways. They are stages. And electricity is the dance that happens when the field starts the music. Nothing magical is hiding inside the wire. Just charges responding together to invisible rules written in space itself. Outline 2. What actually moves inside wires? When you look at a wire, it feels solid and quiet. Nothing seems to be happening inside it. And yet, when you flip a switch, something clearly changes. A lamp glows. A fan spins. A screen comes alive. So the natural question is simple and honest. What actually moves inside the wire? Most people answer right away, electrons. And that answer is not wrong, but it hides more than it reveals. Yes, electrons move, but not in the way most people imagine. They do not rush through the wire like water through a pipe. They do not race from the power plant to your phone in a straight line. If they did, everyday electronics would behave very differently. Inside a metal wire, electrons are already there. Always. They belong to the metal. They are part of the atoms that form the wire. Even when nothing is turned on, those electrons are not sleeping or waiting somewhere else. They are moving already in random directions, bouncing around because of thermal motion. This random motion does nothing useful. It creates no current, no light, no work. It is just noise. Now you turn on the switch. Suddenly an electric field appears along the wire, not slowly, almost instantly. This field gives the electrons a new rule to follow. On top of their random motion, they begin to drift in one direction. Drift is the key word here. The average drift speed of electrons in a typical wire is extremely slow, often millimeters per second, sometimes even less. Slower than a walking ant, slower than a growing plant. Yet the effect of electricity is fast, very fast. So if electrons move so slowly, how does anything happen quickly? Because what really moves fast is not the electrons themselves, but the electric field that guides them. The moment the field is established, electrons everywhere along the wire feel it. Each electron nudges its neighbor. Each responds locally. The pattern of motion spreads, even though the particles barely travel. Think again about a crowd packed tightly together. Each person only shifts slightly. No one runs across the room, but a push can travel through the crowd in a fraction of a second. The motion is collective. Inside the wire, the electrons are like that crowd. But electrons are not the only thing involved. The atoms themselves play a role. As electrons drift, they collide with atoms in the metal. These collisions slow them down and transfer energy. That energy becomes heat. This is why wires get warm when current flows. It is not because electrons are fast. It is because they are constantly bumping into things. In some materials, those collisions are rare. In others, they are frequent. That difference is what we call resistance. So what moves inside a wire? Electrons drift. Atoms vibrate more strongly. Energy shifts from organized motion to random motion. Heat appears. But there is something even more important than particles. What really fills the space around the wire is the electric field. And when current flows, there is also a magnetic field. These fields are not made of matter, but they carry energy and momentum. They shape how charges move. They store and release energy. In fact, most of the energy delivered to a device does not travel inside the wire at all. It moves through the space around the wire, guided by the electromagnetic field. The wire mainly serves as a guide, shaping the field and allowing charges to respond. This sounds strange at first. We are used to thinking that energy must ride on something physical, like a truck carrying boxes. But fields do not need trucks. They are the system. When a motor spins, energy flows from the power source to the motor through the field. When a bulb lights up, energy flows into the filament through the field. The electrons inside the wire move only enough to make that tensor possible. This is why cutting a wire stops everything instantly. Not because electrons were halfway down the road and got stuck, but because the field can no longer exist in the same way. The pattern is broken. This also explains why alternating current works. In AC power, electrons do not travel far at all. They move back and forth. A tiny vibration, yet energy flows continuously. The field changes direction, and the electrons respond locally. So again, the important motion is not distance traveled. It is coordination. Now think about this. If electrons barely move, why don't wires run out of them? Why don't batteries empty the wire? Because electrons are not consumed. They are participants, not fuel. The fuel is energy, and that energy comes from chemical reactions, mechanical motion, sunlight, or other sources that maintain the electric field. The wire is like a dance floor already full of dancers. Turning on the music does not add dancers. It changes how they move. Once you see this, many puzzles disappear. Why lights turn on instantly? Why thicker wires reduce heating? Why insulation matters even though nothing flows through it? Why spacing between wires can affect circuits? So what actually moves inside wires? Electrons drift slowly. Atoms vibrate more intensely. Fields change rapidly. Energy flows smoothly. Electricity is not about objects racing through space. It is about motion shared across a system. A quiet, organized response to invisible rules written into the space around us. And the wire, which looks so simple from the outside, becomes a place where many kinds of motion cooperate to do something useful. Outline 3. Why bulbs light before electrons? When you turn on a light switch, something almost magical happens. The room fills with light immediately. There is no waiting, no delay. You can feel. It feels obvious, so we rarely question it. But if you think for a moment, a strange question appears. How does the bulb light up so fast? If electricity were electrons traveling from the switch to the bulb, then those electrons would need time to get there. And electrons are not fast travelers inside a wire. They drift slowly, often slower than a crawling insect. So how can the bulb glow before the electrons arrive? This question points directly to one of the biggest misunderstandings about electricity. Let's clear the picture first. Inside every metal wire connected to the bulb, there are already electrons everywhere. The wire is full of them. They are not waiting at the switch. They are already sitting near the bulb, inside the filament, inside the wire leading to it. Even before you turn on the switch, those electrons are moving randomly. Thermal motion, chaotic motion, but no useful motion. Now you flip the switch. At that moment, an electric field appears along the entire circuit, not creeping forward slowly, but establishing itself almost at the speed of light. This field changes the rules for every electron in the wire at nearly the same time. Each electron feels a tiny push. The electrons near the bulb do not wait for new electrons to arrive from far away. They respond instantly to the field that now exists, where they already are. They begin to drift. They collide with atoms in the filament. Ion is transferred. The filament heats up. Light is produced. So the bulb does not wait for electrons. It waits for the field. This is the key idea. Electricity is not about electrons traveling from place to place like messengers. It is about fields spreading information and energy across space. To see why this matters, imagine a very long wire connected to a bulb. You flip the switch. The bulb lights up almost immediately, even though the electrons near the switch will not reach the bulb for a very long time, maybe minutes, maybe hours. Yet the bulb does not care. It already has electrons ready to move. Think of it like a long stick. If you push one end, the other end moves almost instantly, even though the atoms in the stick barely shift from their positions. The force travels, not the atom. The electric field is like that push. The moment the circuit is completed, the field rearranges itself, and that rearrangement tells electrons everywhere how to move. This also explains why circuits must be closed loops. If the loop is broken, the field cannot form properly. No field, no coordinated motion, no light. Now let's talk about energy, because light is energy, not electrons. When the bulb lights up, energy is flowing into the filament. But that energy does not ride on electrons like cargo. The electrons move too slowly to carry energy quickly over long distances. Instead, the energy flows through the electromagnetic field surrounding the wires. The field carries energy through space, guided by the shape of the circuit. The wire simply provides the conditions for that field to exist. The electrons inside the wire act like valves. They allow the field to do work locally. They transfer energy from the field into heat and light through collisions. So the bulb lights before electrons arrive, because the important traveler was never the electron. It was the field. This idea feels uncomfortable at first because fields are invisible. We cannot hold them. We cannot pour them into a container, but they are real. They have energy. They have direction. They have effect. Once you accept that, many things become clearer. For example, this explains why touching a live wire can be dangerous, even though electrons are not flying out of it at high speed. The field around the wire can interact with your body, creating currents where you do not want them. It also explains why signals in cables can travel so fast. Internet data, radio waves, and electrical signals all rely on changing fields, not fast-moving particles. And it explains why electrical systems behave more like wave systems than like plumbing systems. The water analogy breaks down exactly here. Water must arrive before anything happens. Electricity does not. Electricity responds. So the next time you turn on a light, notice how instant it feels. That instant is not electrons sprinting. It is a global change in the system, a new pattern of motion forming everywhere at once. The bulb lights up because the electrons near it were already waiting not for more electrons but for instructions. And those instructions travel through space as an electric field faster than any individual particle could ever hope to move. Electricity is not delayed by distance in the way we imagine. It is limited by how fast information can spread through space. And that speed is incredibly high. So the bulb lights before electrons arrive because nothing needed to arrive. Everything needed was already there. All that was missing was the signal to move. Outline 4. Energy flows faster than charges. When we talk about electricity, we often mix up two very different things, charges and energy. We imagine them moving together, side by side, like passengers on the same train. If charges move, energy must move with them. It feels logical. But electricity does not work that way. Energy can move much faster than charges. In fact, in many electrical systems, charges barely go anywhere at all, while energy moves quickly and smoothly from one place to another. This sounds strange, so let's slow down and look carefully. Inside a metal wire, electrons are everywhere. They are part of the material. When nothing is connected, they move randomly, bumping into atoms, going nowhere in particular. Now connect the power source. An electric field appears along the wire. The electrons respond by drifting in one direction. But this drift is extremely slow, often millimeters per second. If you marked one electron and waited for it to travel across your room through a wire, you might wait hours or days. Yet the energy delivered by electricity does not wait. Flip a switch, and energy reaches a light bulb almost instantly. A motor starts spinning right away. A speaker begins to vibrate without delay. So how can energy arrive so fast if the charges move so slowly? Because energy does not ride on charges the way we imagine. The main carrier of electrical energy is the electromagnetic field that exists in and around the wire. This field forms when charges are arranged in a certain way and when current flows. The field fills the space around the conductors, not just the metal itself. When the circuit is completed, the field changes. That change spreads through space at a very high speed, close to the speed of light. As the field changes, energy flows with it. The charges respond locally. They adjust their motion according to the field where they are. They do not need to travel far to transfer energy. They only need to move enough to pass energy from the field to the material. Think about a long line of people holding hands. If someone at one end shakes their hand, the motion travels quickly along the line. Each person barely moves, but the disturbance moves fast. Energy travels through the connection, not because people run down the line, but because they interact. Electric circuits work in a similar way. The energy flow is described by something called the Poynting vector. You do not need the math to understand the idea. It simply tells us that energy flows through space wherever electric and magnetic fields exist together. Around wires, energy flows alongside them, guided by the circuit. So when a device uses electrical energy, that energy arrives through the field. The electrons inside the wire act like intermediaries. They convert field energy into heat, motion, or light by colliding with atoms. This is why energy can flow even when charges move back and forth, like an alternating current. In AC power, electrons oscillate around small positions. They do not travel across the country, yet energy is delivered continuously to homes and machines. The direction of energy flow depends on the fields, not on which way electrons drift at a given moment. This also explains something that often confuses people. In many metals, electrons actually drift opposite to the direction we say current flows. Yet energy still flows in the direction from the power source to the device. The system does not care about our sign conventions. It follows the fields. Once you separate the ideas of charge, motion, and energy flow, many puzzles disappear. Why does a thick wire stay cool while a thin wire heats up? Because in a thick wire, electrons collide less often. Energy flows smoothly through the field with fewer interruptions. In a thin wire, more collisions turn energy into heat. Why can signals travel fast in cables, even though electrons move slowly? Because the signal is a change in the field, not a parade of particles. Why can power be transmitted over long distances efficiently? Because energy is guided by fields through space, shaped by conductors, not carried inside electrons like fuel in a truck. This view also changes how we think about safety. A wire can carry dangerous energy even if the charges inside it are barely moving. The surrounding field can interact with your body and create currents where they do harm. Electricity becomes less like plumbing and more like choreography. Charges move a little, fields move a lot. Energy follows the fields. The wire is not a pipe full of energy. It is a guide that shapes how space itself behaves. Once you see this, you stop asking where the energy is stored inside the wire. You start asking how the field is arranged, how it changes, how it transfers energy from one part of the system to another. And the answer is always the same. Energy flows faster than charges, because energy is not tied to particles in the way we imagine. It is carried by patterns in space that can change incredibly fast. Charges are slow, fields are swift, and electricity works because both play their roles together, each in its own way. Outline. Fields do the real work. When people talk about electricity, they often point to the electrons, tiny particles rushing through wires, doing the work. It sounds reasonable. Particles moving, things happening. But if you look more closely, The electrons are not the heroes of the story. The real work is done by fields. This idea feels strange at first because fields are invisible. You cannot touch them. You cannot hold them in your hand. But fields are not imaginary. They have energy, they have direction, and they decide how everything moves. Let's start with something simple. Place a battery and a bulb on a table. Connect them with wires. The moment the circuit is complete, the bulb lights up. Not after electrons travel from the battery to the bulb. It lights up immediately. That speed is your first clue. Inside the wire, electrons move very slowly. They drift, they bump into atoms, they get delayed. If electrons were doing the main work, the response would be slow, but it is not. What changes instantly is the electric field. The field fills the space around the wire and inside it. When the battery is connected, the field reorganizes itself. This reorganization happens extremely fast. And once the field is in place, everything else follows. The field tells electrons how to move. It pushes them slightly in one direction, not fast, not far, just enough. And when electrons respond, they collide with atoms. Those collisions transfer energy. Heat appears, motion appears, light appears. But notice something important. The energy did not come from the electrons themselves. The energy came from the field. The field is where energy is stored and transported. The electrons are just the messengers that pass energy from the field to matter. This becomes clearer if you think about a motor. When a motor spins, energy is being converted into motion. The spinning does not happen because electrons fly into the motor and push the parts directly. It happens because electric and magnetic fields interact, creating forces that turn the motor. In fact, the motor works even though electrons barely move inside the wires. The field configuration does the heavy lifting. The same is true for a speaker. A changing electric current creates a changing magnetic field. That field pulls and pushes a membrane. Air vibrates. Sound is produced. Again, fields doing work. Electrons responding locally. Even in simple heating, like a toaster, the story is the same. Energy flows through the field into the wire. Electrons collide with atoms. Atoms vibrate faster. Heat comes out. The field supplies the energy. The electrons provide the path. So why do we focus so much on electrons? Because electrons are easy to picture. Fields are not. We like objects. We like things that move from one place to another. Fields feel abstract. But nature does not care what feels comfortable. In reality, fields are fundamental. Charges create electric fields. Moving charges create magnetic fields. These fields interact with each other and with charges. And in that interaction, energy moves and work is done. This also explains why electricity behaves like waves in many situations. Signals reflect, they interfere, they resonate. These are field behaviors, not particle traffic problems. It explains why the shape of a circuit matters. Bends, spacing, and geometry change how fields form. Two wires close together behave differently than the same wires far apart. Not because electrons change their personality, but because the field configuration changed. It also explains why insulation is important. Insulation does not stop electrons inside the wire. It controls the field outside the wire. It shapes where the energy can go. Once you start thinking in terms of fields, the whole picture of electricity becomes cleaner. You stop asking where are the electrons going and start asking what is the field doing here? And that question leads to better understanding. Why does power flow even when electrons move back and forth? Because the field can carry energy without net charge movement. Why can two circuits interfere with each other without touching? Because their fields overlap in space. Why can a radio receive signals without a wire connection? Because electromagnetic fields travel through space on their own. Fields are not side effects. They're the main actors. The wire is a guide. The electrons are participants. But the field is the system. Once you accept this, electricity stops being mysterious. It becomes subtle instead. Rich, deep. You realize that when you flip a switch, you are not releasing a substance. You are changing the structure of face around a circuit. You are rearranging fields. And those fields then push and pull charges in just the right way to make things happen. So the next time you see a glowing ball, a spinning motor, or a buzzing speaker, remember this: the electrons are moving, yes, but slowly, carefully, locally. The real work is being done by invisible patterns stretching through space. Patterns that carry energy, create forces, and make the modern world run. Fields do the real work, and once you see them, you start noticing them everywhere.